So we are continuing with electric current through conductors, part 2. Different types of resistors that we have seen are of two types, the linear and the non-linear. The non-linear varieties include thermistors. Therma implies temperature, so this depends upon temperature. The photoresistor, photo implies light, so the resistance depends upon light. And then we have the varistors, which depends upon the potential difference. Now the linear types are again of two, fixed and the variable type. The fixed ones are carbon composition resistors, the carbon film resistors, and the wire wound resistors. The variable ones include the rheostat, the potentiometer, and the trimmer. Now let us take the carbon composition resistors and the different types of resistances which we see in our labs. We have the resistance box, the rheostat, which is very common, and the carbon composition, which is found almost in all circuits, and the potentiometer, which we see in fans, and the thermistors, and the photoresistors. This is what we had seen last time. Now let us go specifically to the color coding of the carbon composition resistors. So we have resistances, we have a lot of colored lines on these carbon composition resistors. Now what are we going to do with these lines? They are codes. So we have the first line, the second line, the third, and the fourth line here. There may be a fifth line also. Now these are the leads which we can see. Now we have a big table to be understood and remembered. Now if you look at the table and if you look at the colors part of it, the first column, you have black, brown, red, orange, yellow, green, blue, violet, gray, dove, white, for gold, for silver, and no color. Now the colors, or there's the first digit which implies from 0 to 9. The second line implies the second digit which again goes from 0 to 9 depending upon the colors. And the multiplier, the third one, into 10 raised to 0, 1, 2, 3 up to 9, and then for gold and silver it is -1 and -2. And the last column is the tolerance, how much it can bear, how much the resistance can change depending upon external factors. And for brown it is plus minus 1%, for red it is plus minus 2%, for gold it is plus minus 5%, for silver it is plus minus 10%, and no color plus minus 20%. Now how are we going to remember this table? Now look at the first column again. You take the first alphabet of each word. So you have B, then you have B, then you have R, O, Y, and then G, B, V, G, and W up till here, up to white. So you can remember it like this, that B. Roy, Great Britain, very good wife. This is a funny way of remembering, but we remember it very easily. So again I repeat, B. Roy, Great Britain, very good wife. And then you have the gold, silver, and no color. Now let us take an example, the example electro resistors, and then you have the colors coding in your mind. And now we apply the color coding. So you have first color is yellow, the second one is black, the third is orange, and the fourth one is golden. So yellow corresponds to 4 in the table, black corresponds to 0, orange corresponds to 10 raised to 3, and the golden corresponds to plus minus 5%. So the value of the resistance is 40 into 10 raised to 3 ohms plus minus 5%. So it comes out to be 40k ohm plus minus 5%. That means the resistance can vary from 38k ohms to 42k ohms if it is calculated. So we have finding the resistance using multimeter. We have so many resistance in a circuit. We have taken one of them in our laboratory and we have tested them using a multimeter, and we have got the value as 0.97 by multimeter. Multimeter is an instrument which measures the current, the voltage, and the resistances and the capacitance and many other things it does. Out of that, we will take only the resistance part of it, and we have measured it as 0.97. By color coding, also we have found that it is brown, black, brown, so that corresponds to 1 k ohm plus minus 5% with the last one as golden. By multimeter, you get 0.97 k ohm, which is almost the same. Now we have this video in another one, and the link is shown below. So we have here the resistances in parallel now. Now you can take any resistances. We have done different types of resistances. Now any resistances, if you connect them in parallel, then what happens? Let us see. So we want to find an equivalent resistance. Instead of having three resistances over here, we want a single resistance. Then what would the value of the single resistance be? How are we going to calculate it? Now, since these resistances R1, R2, R3 are connected in parallel, the potential difference V is same. The current is different. So you start from what is different. I is equal to I1 plus I2 plus I3. But we know that I1 is nothing but V upon R1, I2 is V upon R2, and I3 is V upon R3. And I is equal to V upon Rp, the effective or the equivalent resistance. So we have 1 upon Rp is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. If you have, you can have it for more than one resistor, more than one, that is two or more. So you can increase the number of resistance, and likewise the formula will go on adding up. The resistance will go on adding up to it. Now similarly, we can connect the resistance in series. Now when we connect the resistance in series, the potential difference is different. The current is same. Whenever things are connected in series, current remains same. We have the same three resistance R1 and R2. So we start with what is different. V is equal to V1 plus V2 plus V3. Again, using Ohm's law, you have IRS is equal to IR1 plus IR2 plus IR3. I gets cancelled, so you get RS is equal to R1 plus R2 plus R3. Similarly, you can have more than two resistors, more than three resistors, and likewise the equation will change. Now let us talk about power. Power is nothing but rate of doing work. So we have the rate at which the work is done by the electric source is called electric power, or the rate at which the energy is drawn from the electric source is called electric power. Now let us frame an equation. So we have power is equal to work done upon time, that is W upon T. Now lo and hold, P is equal to VIT upon T. How is that? Now let us analyze it. So you know potential difference is nothing but the work done per unit charge, or the work done by a charge to move from one place to another. So V is equal to W upon Q, and you know Q is IT, since I is equal to rate of flow of charges, Q by T. So Q is IT, and therefore we can write W is equal to VIT. So we have substituted instead of W, and the TT gets cancelled, and what you get is P is equal to V into I. It is potential difference into current. So it is measured in watt. 1 watt is 1 joule of work done in 1 second, then power is 1 watt. That's the definition of watt. That's all. We'll continue next time.